Doug here again for Bug Amps, and today, very excited. It's the first time I've tested something that I haven't designed and built myself. Well, I guess I did build it, but it was a kit. So this is a Latino ST-120, and it's the very first amp I ever built, and it's a kit, obviously. And it's a variation on the classic Dynaco ST-70, and it's just a little bit beefier. It's got KT88s instead of EL34s. It's got sort of more stack on the power transformer, and the outputs are just a little bit beefier. And so I'm excited to test this guy, and I also wanted to show you guys what we'll be testing it on today. This is a little something that I built. This is a little convenient test load. So the reason I built this was that my test loads always, they were always just like a resistor with wires hanging off of them and like little points where I could like clip in my multimeter and stuff like that. And it was always just kind of a mess, and I was always sort of like swapping around stuff. And so this thing it's just what I needed, what I've always wanted, sort of in a test load. So for starters, it's a variable, so you can adjust it all the way between 0 and 10 ohms. And the cool thing about that is that because it's variable, you can test output impedance with it. Also, it has BNC right on there, so you can connect it directly to your scope. It's got RCA. It's got test points for multimeter right there as well. And so the other thing I did was I put an L pad on the outputs here. That way, if you're testing an amplifier and it has too much signal for like a sound card or something like that, you can just do a 10-to-1. So it's like a 20 dB 10-to-1 pad that's just built right in. And so pretty excited about this little guy. Now it's the wire wound potentiometer here is set up for, I mean, it can dissipate a maximum of 100 watts, but it's inside a case, and the case has like plastic components on it and stuff like that. And so clearly if you like just run 100 watts into this for half an hour, probably it's gonna melt, right? And so it's really meant for momentary sort of sweeps and square waves and max output and stuff like that. And if you're not running it at 100 watts, for more than a couple minutes, then it's probably fine. I tested it at 30 watts continuously, and it held up just fine there. It got hot, but it's just, I guess it's not a power soak. It's more of like a little convenient test load. So that's what we're going to be using today to test the amplifier. And I should say that I've made a few of these, and so if anybody has interest in them, I'm probably going to like put them on eBay or something, just because they're super convenient. And if nobody wants them, then they're going to turn into presents for friends of mine, probably. So I guess I know a couple people would probably find something like this useful. In any case, I also have a pair of KT-120s here, and so we're going to test those as well, because Bob says that you can run KT-120s in this as well. And so we're going to see how that changes the distortion, the power, and all of that kind of stuff. And so pretty excited. I'm going to try and stay impartial on this, but I'm kind of a fanboy since it's like my first amp. Before I knew anything about amplifiers, I assembled this kit, and it's been a great amp. Love this amp, plenty of power, and it was easy to assemble, and it was sort of like my jumping off point into tube amp stuff. So pretty fun. So to make sure we're doing apples to apples here, I have a variac back here, and before each test between the tubes and for the power output, we're going to just make sure that we're at exactly 120 into the amp. That way the air conditioner doesn't kick on or something and cause the wall voltage to go up a volt, and then we would erroneously get different power out of this, because the way these old tube amp power supplies work is they just go up and down with the wall, and then so you put more voltage into them and suddenly you get more power out. And so we would hate to like swap these out and say, oh, such and such making more power, but really it was just the wall voltage fluctuating throughout the day. So we're going to be keeping close eye on that to make sure we're all correct. And we're going to start out with the signal gen and the scope. But like I said, this has a port on it for an RCA, and it's got an LPAD built in. So that means we can also connect it to the laptop. And so we'll do power with the scope and square wave with the scope. And then after that, we'll probably swap out the KT-120s just to see how those do. We'll swap back in the 88s, and then we'll swap over to the laptop and do some sweeps at various power levels to see how it does. So I'm excited to get this all tested. I've never tested this before. I did a preliminary test just before the video to make sure that it was in fact working. I hadn't actually turned this on in a while, so I just wanted to make sure everything was working on it. We're going to adjust it to 50 milliamps is going to be our bias point, and that's going to be constant between the KT8s and KT-120s. So, all right, should be interesting. Let's go to the whiteboard now. I'm just going to do a brief explanation of the circuit. I don't think Bob likes the circuit just like shared willy-nilly, so I'm not going to show you the actual circuit, but I'm just going to do like a top level, sort of a general, what the circuit basically looks like without values and stuff plugged in. Just because it's interesting. It's a good design. It's simple and pretty good design. So let's go. The ST-120 circuit is really very elegant, and so what it begins with is we have a gain stage at the beginning here, like this. Alright, so this is our input, just as you would expect, right? And down here we've got the cathode, and then we've got a resistor, and then we've got another resistor, I think. Now, it's been a while since I looked at this, so I may get the exact specifics wrong, but this is the general idea, right? And the reason there's two resistors down there is because we're going to be inserting the feedback here, right? And up here, we're just going to get some voltages in from the power supply. All these voltages, I can draw out the power supply later, maybe I will, but it's basically what you would expect, simple sort of power supply. So up here is V plus, right? And so then we're capacitively coupled, like this, and we're going to go straight into a long tail pair, and let's see, so we're going to have a leak like that, grid stopper, grid like this, plate, resistor to supply, cathode down this way, and in this one there's a current source, solid state current source like this, and then directly to the other cathode here, like that, and the resistance here, and then supply again. And so B plus down here, right? And then this grid just gets grounded. I don't even think it has a leak or a stopper on it. It just gets straight grounded to the just to ground. And so the way this works, a long tail pair, usually they're drawn differently, but the DC current comes in both ways, like this, right? But the AC current is like this. And so all the AC current, because the current source won't allow AC current across, only DC right there. And so all the AC current flows this way, and so that means that AC voltage is developed here, which is capacitively coupled again, like this. And the voltages are equal because these resistances are going to be the same, right? Same resistances, but they're equal and opposite because we're taking the voltage on the bottom of this resistor and the top of that one, right? So anything that swings through here is going to be equal and opposite. So like this, like that. Okay, so we're capacitively coupled again. Now we're going to the output tubes. And let's see, we're going to have another grid leak, and this one is actually going to be connected to a negative voltage on this one, right? Negative voltage. And then we're going to have a grid stopper. And then we're straight into the power tubes here. Plates. Actually, you're going to have a screen here. So screen, then the plate. Same here. Right? So cathodes. The cathodes on these are going to go through I think a 10 ohm resistor. Pretty sure it's a 10. And that just senses current, so you can set the bias. And these connect together and go to ground. And then screen, and then plate. And of course over here, we're going to have the output transformer, like this. Center tap connected to the B+. And then we also, this is a ultralinear. It can be run in triode too, but it's ultralinear basically. So we're going to take a 40% tap connected to the screen, like this. And then of course the plates connect to the ends of the windings there. And then we have core, magnetic core of course. And then out here we've got secondary, and we've got 0, 4, 8, and then 16 up here. We just connect that directly to the feedback. All right, so there it is. That's basically it. I think the output transformer is a 4K plate to plate, something like that. It might be 4.2 or something like that, but that's basically it. So there you go. I mean, there's really nothing complicated about it. It's really simple. It's a great circuit. Long tail pair is fantastic. Long tail pair has a huge amount of swing, so you can swing lots of voltage, and because it's got a current source there, you're not wasting any voltage across the cathode or cathode resistor there, which means that you've just got an enormous amount of swing available to you on that. And then of course little gain stage at the beginning, nothing special happening there. And then yeah, you just bring it back, the feedback here, and it just linearizes the whole thing. And these are A12 AUs, right? All of these guys right here are 12 AUs. And these, like I said, these are KT8s, KT88s, or they're KT120s, or 6550s, or there's a few other ones that'll drop in there. You could put EL34s in there, but this actually has quite a high B+ on it, so just gotta watch out. So anyway, that's the basic circuit, so let's do some testing. So yeah, let's go. The first thing we got to do is, because this load is variable, is we're going to set the load for 8 ohms. So it's notoriously fiddly trying to measure low impedance. Now I know my leads here are about 0.3 of an ohm, and so I'm going to shoot for 8.3. There's a limited amount of sort of steps you can do on this because it's a big wire wound pod, and so, but it looks like we've nailed it there. If I jiggle my probes, it doesn't change, so that's where we'll start. Now we're going to flip over to AC. That way we can see what the power we're making is and all of that. Obviously we've got the scope as well. So the second thing I'm going to do here is I'm going to plug in the amp into the load with these banana, nice thick wire here, and then I'm going to plug in the scope. Now keep in mind, if you happen to use a load like this, the scope's shield is going to be grounded to earth, and so probably your tube amp is going to have an output that's also connected to earth, particularly if it has loop feedback. That's no problem, you just need to get the right one. And so generally speaking, it's the negative, and so you want negative to plug into the negative here, which will plug in to, which is connected to the shield of the scope. Now this can create a ground loop, and you can avoid this by lifting the ground and not connecting it directly with a BNC to the scope or something like that. You can use a probe or whatever. But for now I'm just plugging it straight in there because it's going to work just fine like that, I think. And I want to make sure that I've got a little L pad here, but it's just going to be on, so this is going to be reading the correct voltage. I've already set this up. I'm going to turn it on now. We've set that up so that it's running 50 milliamps per tube, and so yeah, we're just going to see how we do here. We're going to see what kind of power we make. I've got the variac back there. We're going to make sure that it settles in at exactly 120, or as close as we can get to 120, going into the amp after it turns on and gets all the current gets going and everything like that. And then after that, we're going to give it some signal and see what it does. So I'm excited. It looks like it's on. It looks like the current is flowing because the power going in has dipped a little bit. That's just dropping across the output impedance of the plug that it's plugged into, of course. Everything has output impedance, I guess, except for like very well regulated stuff, which your wall is not. Alright, so looks like we're at 120.6. So I'm just going to bring it down a tad so we can just be apples to apples here. So now it's at 120. Now that's going to change. I don't know if you can see that, and probably you can't see that on the camera or whatever, but obviously once the amp is under load, it's AB, AB1 class amplifier, so it's going to pull more current once it's under load, and that's going to pull the wall down a little bit. But we're only shooting for 120 in at idle, so don't worry about that. Alright, so let's see, we're all plugged in. We've got the amp plugged in to the load, we've got the multimeter plugged in and the scope plugged into the load here, and we've set it at 8 ohms. So let's give it a little bit of signal here. There we go. That's looking pretty good. And we're just going to bring our signal up until we get 1 watt. So we're looking for 2.83 is what we're going for. So we've got 2.25 here. And just go on up. 2.831. Very close. So that's taking 0.53 volts peak to peak in to achieve. Now we trust this is the meter, right? And so the scope has a little bit of like a RMS function built in, but it's a little bit fiddly. It depends on like what range you're on, it'll change. I think that it's just not as accurate as a meter, right? Especially at 1K, which is what we're starting at. We're starting at 1K. We're going to do our testing at 1K. When we do sweeps later, then we'll be testing at all the frequencies, right? But we're just going to begin our testing at 1K here. And yeah, so that's looking good. No problems there. We could have a quick look at our square wave here. And that looks nice. It's got a little tiny bit of ring, but that's going to be way outside of the audio band right there. And the rest of it looks pretty square. You can see it's got a little bit, just a touch of a slope. You know, it starts a little bit higher here, and it's a little bit lower there. That's going to be a little bit of low frequency roll off. Okay, but it may not be that big of a deal. We'll check obviously when we do our sweeps. We're going to see all the roll off and all that kind of stuff. But for now, that looks pretty good. I mean, it's obviously feedback is working correctly. The transformer is working correctly. Everything is looking good. Like that little bit right there is nothing to worry about. So let's go back to our sine wave here. And let's just see if we can see how much power, because we're looking to see how much power it can make at 1K. Now this amplifier, it's a 120, means that it's supposed to be able to do 60 per channel, right? And we haven't actually tested this before. I did a quick preliminary test before I did the video, but you know, getting close to just a normal test here. Now we've gone up from 2.83 to 2.54 here. So maybe the amplifier was not completely warmed up. So let's bring it back down to, that's 2.8, 2.83. I should probably have waited a little while after I turned it on. 2.83, 2.82. All right, so there we're back at 1 watt again. All right, so now we're just gonna see what we can do. So let's turn the range down this, because we're gonna need plenty of range. Let's go to town here and see what we come up with before it clips. All right, so there's clipping. So we're going to back it off right about, that's like the onset of clipping right there, and we're at 22 RMS. All right, 22 RMS. Let's do the math on that one. So it's 22 times 22 divided by 8, and so that's good. I mean, it's making power. It's making just about exactly 60 watts, 60.5 watts there before clip. And of course, a lot of people will spec an amp at something like 3% distortion or 5% distortion. And of course, that's well into clipping. And so, you know, if we ran this just slightly into clipping, for example, like right here, that's probably like 5%. And now we're at 22.7. So let's do 22.7, just to be fair. 22.7 times 22.7 divided by 8. And so that's 64 and a half watts or so. And so it's right on target at 1K. Now remember, this is one channel driven, right? Also, our wall has dipped a little bit here, it looks like. Just a tad. No, it's basically bang on. And so, so it's making power at 1K. Now, of course, that's one channel driven, and so if you're going to drive both channels simultaneously, it's probably going to drop some amount of watts, right? But still, because it's making 64 at probably, what, 5% distortion or something like that, I'm going to call this specification met. You know, it's making the correct amount of power here. And so that's pretty cool. And so square wave looked pretty good. It's making power at 1K. We've got wave controlled for our variables here. We're at 50 milliamps. So what I'm going to do now is I'm going to swap in the KT120s, and we're going to do this again. We've got the KT120s in here, and biased to exactly 50 milliamps per side, per tube I mean, and we're exactly 120 at the wall before loading down the circuit. So let's now see, just see how we do. Okay, looks like right before clip is 22.81, 22.8. 22.8. All right, let's figure that out one. 22.8 times 8. All right, so that one, that's before clip. So this is in comparison to our first measurement before, where it was just before visible clipping, and we're doing about 65 watts. And so that's an increase of about a little bit less than 5 watts, looks like. And so now let's do our guesstimated sort of 5% distortion point here. Go up until, so that's probably 5% distortion there. Just visible clipping, and we're at 23.35. Okay. Okay. So now that's gotten us up to 68. So I think the previous one was 65. 6, 7, 8, 3. So yeah, it looks like just swapping in these tubes has given us a little bit more power at 1K. Now whether that translates into more power at other frequencies, the output transformers may not be able to handle that at lower frequencies, or who knows. But you know, obviously both channels driven, they'd both be asking for more current, and so that power might evaporate in a situation where you're driving both channels. I don't know, it's hard to say. But I did notice that these tubes require a little bit more negative bias on the grid to achieve the same bias point. And so what that means is that the gain of the tube is probably a little bit lower, and they probably, I don't know, like you can swing, you have to, like I said, the gain's a little bit lower, you have to swing a little bit more into them. So in an amplifier that's limited by the gain of the phase splitter, for example, might not benefit from a pair of KT120s over a KT88. So there's that. Also, if you look at the plate curves for these tubes, I think that these are flowing a little bit more current at 0 grid volts than KT88s, and so that's probably where that extra power is coming from. In any case, that was an interesting test. And so now we've done, let's see if the square wave looks any different. So let's go back to 1 watt. we'll just crank it down to, let's see, let's bring it down to 1 watt and we'll look at the square wave so it's apples to apples, because the last time we were looking at the square wave, we were looking at 1 watt. So 2.8 or so, and square wave. Square wave looks identical, so swapping those other tubes in. In fact, you know, it's interesting. You know, my memory's not that good, but it seems like maybe there's a little bit less of low frequency roll off, but we'll see that much more clearly once we start doing the sweeps, right? Oh, here's another thing I wanted to show you about this little load that I've been talking to you about. You can see that I can turn the output off, or I can bring it down. So that's not a good example. Let's go back to a normal sine wave. And so right now we have, let's see, 2.8 volts, right? And so if I switch this into its padded mode, then we should get something like 0.28, right? But we're getting 0.26, so it's close, right? So it's about 10 to 1. So that's going to become handy when we plug it into our sound card in a minute here. All right, and so that's that. I think because we've got the 120s in, we're going to start our power sweeps at 1 watt with the 120s, and once we get that data, we'll swap back to the 88s and see how we do. All right, let's go. All right, so we've swapped our source. I forgot I got to turn on the amplifier. I actually took the Variac and I put it down under the table because I was worried it might couple hum. Because Variac has got a big old inductor in it, so it might couple hum and mess up our noise measurement. So let me turn on the amp. And I'll still be keeping an eye. I've got the multimeter over there, so I'll be still making sure we have exactly 120 volts in. And this has not been changed, so this is still measuring 8 ohms. Obviously, we could measure anything we'd like because it's variable. We could do 4 ohms or 6 ohms or anything like that. Later, we might measure the output impedance too, because we can do that with a variable resistor like that. You can see we're already getting some power supply noise here. That's typical. As the amp is warming up here, we'll see how that does. Right now, I have this in 1-to-1 mode. The load is, and so later on when we do full power testing, we'll switch it down into the padded mode. That way we can run this thing flat out without messing up the input here. So sometimes you create a ground loop in measurement because you see the computer will be referenced to ground at the input jack and it will be referenced at the output jack. And so sometimes you can lift the ground a little bit and you can see the difference that's making here. So if I lift it, so that hum just drops a little bit. It's not a huge ground loop problem, but it's just good to keep that in mind when you're doing noise measurements like this. Alright, so let's start generating a signal and see what we're getting here. I'm going to start generating 1K. See it pop up there. We're going to go up to 1 watt output, so we're looking here to see 2.8. 2.83 is what we're shooting for if we can get it. 2.825 is probably as close. Oh, 3, 2. That's how we're gonna, as close as we're gonna get. Now we're gonna turn the input of the sound card up until that's exactly 80 dB, because that's just because I know that gives us the best signal to noise possible on this particular setup. Okay, so you can see that we've got our signal here. Let's look at the distortion here. We'll bring up the distortion panel, and yeah, it's looking great. So our distortion is low at 1 watt, 0.01. It's hovering between 0.02 and 0.015, and that probably means the tube amp is still warming up a little bit. And that's at 80, and we're looking at our noise down here. Our noise is around 0. It's probably like 10, 5. It's probably like 8 over 0 there. And so we're looking at a signal to noise at 1 watt. It's pretty good. For an amplifier that has sort of a very simple power supply. So that's like, it's a little bit over 70 dB signal to hum, at 1 watt. So reasonably quiet amplifier. You can see this has crept up a little bit, 8.4. See if I get it back to 2.83. It's probably as close as we can do. And so, yeah, 1 watt performance at 1K, as you would expect with a loop feedback amplifier. Looking great. Settled in at 0.016 or so, which is really nice with signal to noise ratio. Now, what we could do to give this thing the best benefit of the doubt as far as signal to noise goes is we could turn off the gen. Yeah. And we could unplug and short the input in question here. Okay, so we're unplugged it. Let's short it. Right there. And that hasn't helped us out very much. It took our 120 down, but our 60 is still quite. Let me see if I do this. So I've put the ground back. So really, shorting the input isn't giving us a different noise floor than just having it plugged in normally. So we'll just go back to how it was. But still, that's pretty good. It's not bad. Yep. Yep, there's our noise floor. You can see it hasn't changed a lot from the shorted. So that just means the output of the Focusrite is quiet enough. That it's not, obviously the output of the Focusrite is very, very quiet, so it's not significantly different than a shorted input in this case. Great. All right, so now let's switch in the pad so we don't blow up our sound card, and turn our sound card all the way down, and see if we can get back up to the 22 odd volts that we were getting under max input before. Okay. Just crank it right on up. You can actually hear the humming. That's the actual output transformer there. Okay, so now what do we say? This is 3%, 4%. 3 or 4% is right here. All right, so that's as high as we're going to measure right there. Actually, I should have set that to 80, I guess. So that's as high as we're going to measure, and we'll put the input of that up to, let's see, bring it down right there. And so that's about 4% distortion, so that's going to be our max level. Okay. Now what we're going to do is we're going to bring it down using the audio interface here. We're going to slowly bring it down until we're near 1 watt, then we can do our sweeps. Okay, close. We're going to go below 1 watt and then turn it up to 1 watt. And the reason we're going to do that is that we can drive the amp in our sweep test. We can drive it all the way up into clipping. We don't want to clip the crap out of it, but we want to, we want to get it pretty clipped so we can see what it does. 2.83. We're going to try and get as close to 1 watt as we can. All right, so there we are at 1 watt. Negative 22. That's where we're going to start our sweeps. Okay? Negative 22, let's do it. Bring it down. 22. Okay. Let's see if we got this set up right. Yep, that's looking good. We're right here, you can see we're right at 1 watt. Now the noise performance will suffer here because we've got a big L pad in the way. So we're going to ignore noise. The noise that we previously looked at in FFT, that's the real noise. So if we go to the distortion panel, yeah, I've already deselected noise. So we're just going to deselect noise completely for these tests. We're only looking at distortion. And we're going to look at the frequency response. And so here's 20. We're gonna do, I think we did a 20 to 20 sweep, is that what we did? And let's scroll up here, see if we can find it. Oh, it's gonna be lower, remember, because clipping is at 80. So here it is. Yep, we started at 20 and we went to 40K. Let's zoom in. All right, so this is that little bit of low frequency roll off that we saw in the square wave. So at 1K, reference to 1K, 61.7, and then down at 20, 61.3. So it's not huge. It's less than a dB, you know, so it looks huge when you zoom in on it like this. It looks like a big roll off, but it's amazing how you can see that on the square wave, that we would expect to see a little bit of low frequency roll off, but this low frequency roll off at 1 watt is not audible. You'd definitely be struggling to hear the difference between 0.7 and 0.3 dB. I don't think I could do it. Not that I'm not saying I have great ears or anything, but it's not really a big deal. All right, so we'll just label that 1 watt. And now what we're going to do, and I won't make you sit through this, but I'm just going to go up by 1 dB increments, and I'm just going to go all the way up to that -3 where we were clipping. All right, we're just going to sweep all up, and then we're going to look at it all in order and see the performance of the amplifier. Now this is interesting here. We should look at this distortion panel, or this distortion measurement, because you can see here that 1K is sort of the best case on this amplifier. If you go a little bit lower, down here at 30, now we're looking at 0.6% distortion. This is typical for a tube amplifier because the output transformer is going to have lower inductance at lower frequencies. It's going to have more issues, so this is typical rise. And then up here we've got a little bit of a rising fifth that comes up here, and by the time we get to 10K we're at 0.07. Now these are not high distortion numbers, these are still very low, but I just want you to see that like measuring distortion at 1K is not the whole story. But this is good performance for an amplifier, tube amplifier. I've definitely seen much worse than this. It's looking really good. Alright, I'm going to do those sweeps now. So I've just finished up the KT-120 measurements, and I thought I would pause here and just sort of go over them before we do the KT-88 measurements to compare. It's pretty interesting. So you can see these are starting at 1 watt, going up in 1 dB increments all the way up to the maximum one was a pretty clipped 74 watts. And you can see, I don't know if you can see this right here, I mean I guess you can because I've got the cam right on it. This little dip right here, that was at the maximum, so that happened at between 25 and 40 hertz at 74 watts at 1K, so less than that down here. But what happened there was the rectifier actually arced over due to overcurrent. And so my friend Pete is he's gonna tell me that he was right about this. And so Pete, you're right. But yeah, so what happened there is the inductance of the primary of the output transformer is insufficient here probably to handle this kind of power at this frequency without overcurrenting the rectifier. Remember, this is just with one channel driven. And so the recommendation here would be, you know, don't try and do 30 hertz at 74 watts with this amplifier. I mean, that may seem obvious and stupid in retrospect, but this is the kind of thing that's cool to sort of just see and be interested in. Also, you can see that there's no power compression except for until the last clipped reading. There's no power compression up until the reading before that was 67 watts, and so it's really hanging in there well till 67 watts and being very linear, except for down here at the low frequencies. So at the low frequencies, the output transformers start to give up at about 40 watts or so, and below 30 hertz, we get a little bit of roll off. 6, 7, 8, it's about 2 to 2.5 dB of roll off at low frequency at very high power levels. And honestly, that's, you know, what do you expect? You can't get something for nothing. And although these are pretty big output transformers, the size of output transformer you need to deliver 74 watts at 30 hertz is pretty enormous. And so all said and done, This is perfectly acceptable performance for this. Just keep an eye out that you can. I mean, this is a JJ GZ34 or something like that. A different rectifier may perform differently there. So this is just my personal experience here. Also, let's look at the distortion. Distortion is well controlled. Oh wait, I want to. So here we go at 1 watt. This is what we were looking at before, and we're just going to go up. We're going up by 1 decibel in increments, and so we'll just keep this at 1K, so we can see the measurement down here. So you can see it rises at low frequency and high frequency, but actually that evened out as the power level went up. So here we go: 1.27 watts, 1.6 watts, 2 watts, 2.5 watts, 3.2 watts, and so you can see that the second and the second and the third are coming up. We got a little bit. This is probably, I don't know what that could be. That could be crossover distortion perhaps, or just some residual loop feedback amplifiers sometimes have high order. But that goes away in a minute here as we get to 5 watts, 6 watts, 6.3 watts here, 8 watts, 10 watts, 15 watts, and by the time we get to 15 watts, it's all second and third, and all of the high order distortion is sunken down. So this is sort of the sweet spot of the amplifier here. And so, scroll down here. Now we get up to 20 watts. So this is right in the middle of the power range of the amplifier. We're at 1% distortion here, but you can see it's starting to get a little distorted down here below 30. That's the output transformer is giving up. But look, the output distortion is quite nice and even all the way up through high frequency, and so that means the output transformer is a well-designed, has the correct type of interleaving and everything like that. Capacitance between windings is pretty well balanced as we go up here. And then you can see the second and third are about the same, and now we're up at 32 watts. You can see that the third is increasing down here. That's the output transformer giving up. 41 watts. This is where we said that we started to get power compression in low frequencies, and we're rising distortion here below 40 hertz. Now up to 52 watts, and so that's like basically close to maximum. Now here's 67. This is that point of visible clipping probably that we saw on the scope. 3.2% distortion, still not horrible. Obviously you wouldn't want to play it like here all the time, but for like a transient, a kick or something like that, not so bad. But you can see that below 50, the distortion starts to skyrocket and the frequency response begins to fall off. And then here is our rectifier shorted out, 74 watts down here between 20 and 30 hertz. It recovered quickly though, and you can see the rest of it, we're at 4%. And it's still, even at 4%, it's pretty well behaved, although the 5th harmonic and the 7th harmonic are above the 2nd and 3rd now, so this is kind of distortion that you wouldn't want. It's not going to be a good sounding distortion at this point. But I mean, we're pushing it way beyond what is expected here. So that's that. So I'm going to swap in the KT88s. We'll do this all over again. So we got all the way through the sweeps with the KT88s, and this time the final sweep did not arc the rectifier. And so I guess that's one point in favor of KT8s over 120s if you really want to push it at low frequencies. Although we didn't make the same power, the final sweep on this one was only at 69.6 watts. And so let's have a look at the SPLs here. You can see a similar thing though. The final one is more compressed perhaps, so you're getting a touch more power out of the 120. We still have this low frequency, sort of, it's not keeping up at low frequencies below, let's say, like about 35 hertz. And that's starting at, let's see here, that's the teal one. So starting at 30 to 40 watts, below 35 hertz, it'd start to get a little bit of power compression, and obviously the distortion is going to go up. So let's go back and start at 1 watt and see how we did. So you can see that the 1 watt distortion measurement, now I'm going to be comparing these, I don't have them right here to compare one to the other. Maybe I should try opening the other ones as well. That way we can look at them side by side. So open up the KT-120s as well. Here they come. I'm going to also animate these. Oh, I don't have enough tabs. Okay. So I'm gonna open up these and I'm gonna animate these side by side so that you guys can get a really good idea. Of what's going on here, but we can at least look at the 1 watt version here. Whoops, wrong slider. All right, so let's slide back up here. So here is the KT88 1 watt performance here. You can see at 1K we have a distortion of 0.16. Now remember, tubes are all different, and my particular tube pair might not be that well matched or whatever, and so, but if you look, this is interesting, the KT-120 at 1 watt, the distortion looks way different. So the distortion at 1K goes from 0.1 to 0.027, right? But it has that sort of scooped out where it's higher and lower at the ends, whereas the KT88, it sort of doesn't have that at all. It's more consistent in distortion, although the overall distortion is higher. All right, so let's go up to, let's say, I wonder if it loaded 5 watts. Let's do 5 watts. So here's 5 watts. We're looking at the KT88, 0.318. No, I think the KT-120 5 watt loaded. Let's see. Yes, here we go. So that's 5 watts. So 0.2. The 88 is more consistent. You can see that the higher distortion is very low, whereas the lower distortion is high. That's usually considered preferable, right? And so if we go to the KT-120 at 5 watts, higher order distortion is coming up in here, right? We've got, what is that? 4th and 5th, up there with the 3rd, right, at 5 watts. What's the highest one that we loaded for 120? 8 watts. So let's look, 8 watts. This is KT-120 8 watts, 0.4% distortion. Okay, so let's go look at the KT-88 at 8 watts. Here we go. All right, once again, the KT-88 looks like the distortion is slightly higher at 0.5%, but the distortion is all low order distortion, and the higher distortion is very well controlled. So 8 watts with the 120, sorry. Let's see, is lower distortion total distortion, but what more of the percentage of that distortion is these higher order components. And so, you know, it's kind of hard to say which one's better. In any case, I think the last thing we're going to do now, I know it's probably been a long video, is we're going to measure the output impedance of the amplifier. And I'm going to show you how to do that using this handy little test dummy load here. So you can see how to do that. So I'm going to get that set up. Okay, so the way this works is you measure, first you load the output of the amplifier with an arbitrarily large resistance. For in this case, I've just done 1K. because compared to the output impedance of the amplifier, 1K is arbitrarily large. And then what you do is you set it so it's at a known voltage, AC voltage. So right here I'm trying to get it for almost exactly 2 volts is what we want. Yeah, that's pretty close, And so now what we're going to do is we're going to plug the amplifier into the load, like that. And we're going to plug our multimeter into the load, like that. Very good. You can already see we've come down from 2 volts. Now this is going to include the series resistance of the cable, but it's very low. It's a nice thick cable. So we've already come down to 1.15 from the 2 that we were at previously, right? And so let's just make sure we're still at 2. I'm going to pull one side of this and measure it. 2 RMS. All right. So let's plug this back in, right? And so now we're at 1.15, and we're just going to turn this down until we get to exactly 1. Down we go. All right. That's not quite it. There. Okay, so now let's turn off the amp. This is on the 8 ohm tap. It'll be different on the 4 ohm tap. It'll be lower on the 4 ohm tap than the 8 ohm tap. So go on the 8 ohm tap, we unplug this, and now we're just going to measure the resistance of our load, because that will be our output impedance, and it's 6 ohms. And so this is interesting. Usually a loop feedback amplifier is going to have a very low output impedance. However, this amplifier doesn't have a lot of loop feedback. It's just got some. And so it's got a fairly high output impedance on the 8 ohm tap. And in my opinion, that's desirable, and because that's what gives tube amps a lot of their sound, is having a slightly higher output impedance. If you found that objectionable, you could run it on the 4 ohm tap, and that would probably bring your output impedance down to 4 ohms or something like that. But yeah, so it's got a fairly high output impedance of 6 ohms on the 8 ohm tap, and that's going to cause it to interact with speakers. The bass will be a little underdampened, which I like personally. And you're going to change the frequency response of the speaker a little bit, where the response of the speaker is going to follow the impedance curve a little bit. And so some people like that, some people don't. It's different for different speakers. But yeah, so that's interesting. So we were able to find the output impedance of the amplifier is about 6 ohms on the 8 ohm tap. So another fun thing about having a little load like this that has a variable load. So you just crank it around and fiddle it. We could potentially test an amplifier at every different output load. That would be interesting, you know? Could do it. Anyway, that's it for this test. In summary, it's a good amp. I like it. I think probably I'm going to look more closely at these distortion measurements, but probably it's not worth running 120s in it, just because the rectifier probably can't take it, and the 88s seem to work just fine. All right, that's it.